Hi, this is lesson 2 on thermodynamics. So I know we've already done a lot of this in class, but if we are going to go a little bit deeper into thermodynamics, we really need to make sure we've got this down pat. So we're going to be going over today the first law of thermodynamics again. Just make sure you're absolutely cool with all of this because it will make what follows so much easier. So the first law of thermodynamics is really just sort of defining terms, laying out our stall and saying what is it exactly that we're talking about here. And it's also sort of taking apart energy into 3 different types of energy so we can refer to each of them quite easily. Those 3 are U, which is internal energy, Q, which is heat energy, and W, which is work done. Okay? W in thermodynamics basically means any type of energy that we wouldn't normally call heat. So kinetic energy, something useful that you can get out of the system. That's the W bit. So what does the first law of thermodynamics say? It says the change in internal energy, so any sort of change to the internal state of a system, will be equal to the heat that we put into the system minus the work done by the system. And the minus bit can be a little bit fiddly, but we'll get to that. Let's start with the internal energy. There are 2 different parts to internal energy. They are the kinetic and potential components. The kinetic energy is a representation of how much the particles are moving around, what we would normally call temperature. So absolute zero, the lowest possible temperature, is the point at which the kinetic energy of the particles is 0. They're no longer moving. So that's the kinetic part of the internal energy. It's just a measure of temperature, simple as that. The potential part is a measurement of how much electric potential energy the particles have, which of course you will know is going to be dependent on how far apart they are, or another way of putting it, it's the state. Is it a solid, a liquid, or a gas? Solids, the particles will be as close as possible, which means they'll have the least potential energy. Liquid, they're a little bit further apart, so they'll have more potential energy. Gas, they're really far apart, so it's got masses of potential energy. So as something goes from a solid to a liquid to a gas, the potential part will increase. Similarly, as something heats up, the kinetic part will increase. So as we put more and more heat into something, this Q part, the U will go up for both the kinetic and the potential. So both of these will increase, which is great because that's what the first law of thermodynamics is saying. Also, we should be aware that the difference in particle separation between a solid and a liquid is much smaller than the difference in particle separation between a liquid and a gas, which would make us think it takes more energy to transition from a liquid to a gas than it does from a solid to a liquid. And we should already know this from our latent heat of vaporization and fusion. And you should all be aware latent heat of vaporization tends to be a lot greater than the latent heat of fusion. So that all works lovely jubbly. Now we've got the Q part. This is heat. Heat in thermodynamics just means heat energy going in and out of things, normally transferring internal energy from one system to another system. So heat in thermodynamics is its own separate thing that we call Q, and there's going to be lots of Qs going in and out of things for the rest of this, so just keep an eye on that. Finally, we have W, which is work done by the system. So, if the system does work, if whatever it is that you're heating up or cooling down pushes out on something, crushes something, moves something, does work, then that energy's got to come from somewhere because of conservation of energy. And it'll either come from the U dropping or because you put heat in. So, let's think about this. If we're keeping something at the same temperature or same state and we want it to do work, we're going to have to put heat in. Or if we're not putting heat in and we want it to do work, we're going to have to let it cool or change state down from gas to liquid to solid. So something in the system's going to have to give if we want work to come out of the system, which would make sense because of conservation of energy, never getting something for nothing. Now sometimes, instead of the system doing work, we actually do work on the system. If we were to take a gas and we were to crush it, we'd be putting energy into that system, so we'd expect delta U to go up and for it to heat up, and this is exactly what we find. When we crush a gas, when we do work on a gas, they get hotter, but when we let a gas do work and expand, they get colder. So, that's the first law of thermodynamics. Make sure you know what each of these three terms mean. There's a question underneath, and I'll return tomorrow with something just a little bit more complicated, but I thought it was important today to really just make sure we were rock solid on this. Okay, see you later in the week.